I've prepared here on this side of the board, and I think I should do it just about every time, a summary of the ideas that I already discussed in the previous lecture. Some very simple ideas. Although I made a big deal about locating an object or an event in the universe, in some coordinate system that I have quite a bit to say about the measurement of things and the deep meaning of the measurement. I'm going to ask, once again, that you not let that idea go. That when you have a spare moment in all of the problems that you're solving and the labors that you undertake, that you think deeply about the meaning of things. And one of the most interesting things is that ours is a universe of change. That once I look around and identify the positions, locations of everything in the universe, I discover that if I turn my back, that the universe will evolve, that the positions will all change. And so I created, to describe that, the displacement delta x, which is simply the final position minus the initial position. Now, in this description, I'm doing things in a one-dimensional way. But we agree that if I wanted to do things in 3 dimensions, I would simply add vector components to that. And so there's no real great information in doing it in 3 dimensions from scratch. So we stick to the one-dimensional description and then simply expand our understanding. We'll have an opportunity to do that in just a bit. But even as I observe the universe and its changing positions, I discover that the rate at which various things in my universe change their positions changes. That some objects move more rapidly than others would be a really shorthand way of expressing that idea. So I devise a quantity that describes that. Physics is a description of the universe. And that quantity is the velocity on average, which is simply computed. The displacement divided by the time. Now, displacement is a vector. I can displace in the positive direction or displace in the negative direction. And since velocity on average is defined in the context of displacement, it too is a vector. But it's quite simple, isn't it? If I have a positive velocity, it means I'm moving in the positive direction. And if I have a negative velocity, it means I'm moving in the negative direction. That's quite easy. So I have a little trouble with notation. I've made a note of my notation struggles here. Is that I can't go on forever and ever writing harpoons on every damn thing that I invent. And so I have a tendency, and many would call it a bad habit, but I have a tendency to leave the harpoons off. But I want to suggest to you that a perfectly good notation for this might be that I write a V with a harpoon on top of it, which reminds me, in fact, that velocity on average is a vector. And you might think, well, of course it's a vector. I don't need any notation. I agree. But if we're being sticklers, we may say, no, you must write. Someone's going to say, you must write. There are sticklers for notation out there. But also this quantity today, I'm going to describe this quantity in the context of, instead of the average of the quantity, I want to know what is the quantity at every instant. So maybe I need a notation that calls that out. So I might write the V with a bar over the top of it. Notice it has no harpoon's prongy thingy on it. And that means that bar over quantities very often means the average. Although in elementary particle physics, it might be describing the antiparticle when there's a bar over top of it. So we have to be careful about notation. But I want to say that any 3 of these are adequate to describe it. And we agree that the average velocity that I've described is a vector quantity. There's a little bit of algebra that I could do when I appreciate that delta x is the final position minus the initial position. I could solve this around for x, and I've done this here just for our enjoyment, that the final position, or I might say some position in the future, is equal to whatever the position is now plus the average rate at which the position changes multiplied by the time. I read that equation as language, a description of the nature of things. And it's pretty exciting because I can predict the future. That's pretty nice. That's a really good trick. I can know where a thing will be in the future by knowing where it is now and the average rate that it changes. We say, well, Scheidly, this is a poor demonstration because you only know on average. You don't really know the details of what happened in between. Well, yes, today's lecture is all about fixing that. So I can understand the nature of the behavior in the instant. Much, much better thing, and I'm interested in knowing. But many will look at this equation. It's also okay that this is an equation that I might bank to solve problems. So I might use that as for utility of solving problems, although I imagine that as our physics becomes more sophisticated, we'll abandon that in favor of equations that are more general and more instantaneous. So I'd better make a start with a graph that I'm going to begin with a graph that was sort of at the end of last lecture. Imagine that I have I was about to say trajectory, but that's not specifically what I mean. A graph of position as a function of time that is somewhat more sophisticated than linear. And for the sake of continuity, I'll draw it just as I did in the previous lecture. I'll just make a curve like this. I know, because of the way the average velocity is defined, that it's very much like the slope of things. I learned very early on in a little math class, it was adorable, that the slope of a line is the rise of the line over the run of the line. And so when I see delta x over delta t, if I think of that as rise over run, that's completely appropriate. Well, the slope of this graph clearly changes. Early on, when t is small, the slope is quite steep, and that would imply that the average velocity is quite high. And then later on, the slope gets quite shallow. In fact, the way that I've drawn it in this particular version of it, we see that it's approaching zero, and perhaps the average velocity will come to zero and the object will stop. Being able to look at the graph and interpret how the slope goes is a very useful skill for the physics student. Nevertheless, what I suggested is that I don't really know all of this when I'm talking about quantities on average. I want to be very careful to appreciate the fact that I don't really know any nonsense that happened in between. I don't know what kind of tomfoolery happened. It could be a very strange path. I've made it sort of reasonable here. But that curve exists only in our imagination. What we have is measurement. We have observed the location of the object here at the beginning of the thing, and this is the initial position. I'll mark it on this axis here as x naught. The initial position, which happens at an initial time, t naught. I very likely am going to call t naught 0. Very likely going to say that t naught is equal to 0 because it conveniences my algebra quite a bit to not be carrying t naughts around anywhere. And of course, anytime I do an experiment, I'm very likely to reset the stopwatch before I press the button to measure the times at which events or processes or phenomena happen in nature. So I made that measurement of position, and later on I'll make another measurement of position over here, and I'm just going to call that x in the future. It could be any x, but in this case, I mean that at a particular time t, I've measured a particular position x. Seems okay. And that's the only information that I have. Remember, the curve lives only in my imagination. And so the only thing that I can do in terms of imagining the behavior of the thing is to draw a line from this initial position on the graph to the final. And I have to draw the line right through. Oh, not bad. Well, that's meant to be straight. So continue to use your imagination and realize that that line goes straight through. And so the average velocity of this process, as we talked about previously, is going to be the rise of this line over the run of the line. And so along the time axis here, which in math class is typically the x-axis, but along the time axis here, I measure a certain interval of time, delta t. And along the vertical axis, which in this case is the x-axis, along the vertical axis, I'm writing the position. So the rise on the vertical axis is going to be delta x along here. Now, inadvertently, delta x. And so I see that the slope of that line, which is a positive slope clearly because of the way that I've drawn the thing, is the average velocity and ignores all of the change that happens between those 2 points. Well, what I would like to do today is to perfect this idea and become more expert, or more, I should say, more precise in my understanding of the velocity at every instant in time. My goal, what I would like to have, is I would like to be able to claim that you can say, Scheidly, at this time, at 5 seconds, and I can tell you at 5 seconds what the velocity is in that instant, not on average, but the actual velocity in that instant in time. So imagine the instant that I suggest is sort of in the vicinity of here, some point sort of midway along. And I want to know what is the slope at this point. Well, the slope at this point differs potentially from the average because, as we see, early on the slope is quite steep and later on the slope is quite shallow, and at any point in between it's a different slope. And we say, well, I have an idea. we'll get a better idea of the slope at that particular point if we evaluate the average of the slope in a region around that point. That is, instead of a large interval of time, delta t, let me consider a small interval of time along the time axis. That is, I guess, the way this graph is drawn, to the left and to the right of that point. A very, very small interval of time. Then along the vertical axis, I'll choose a very, very small interval of position. And that is like zooming in on the graph is the best way of describing it. Imagine you take your mouse pointer and you select that little region and hit zoom, and now it zooms in. Well, any curve that I look at, if I zoom in sufficiently, becomes a straight line. Imagine you go on your computer and you draw a circle, but then you go to the curve of that circle and you zoom in, you zoom in, you zoom in, you zoom in, you zoom in. Continual zooming on that eventually becomes a very straight line. And so I can compute the slope of that line in terms of the rise and the run here. I need a notation that's going to express that instead of using a large interval, delta x and delta t, I'm going to use a small interval. And the notation for that is a lowercase d. That is, the interval along the time axis I am going to call dt. And along the vertical axis, I'll call that interval dx. Now I'm impressing upon you this, as I have done before. There is physically no difference at all between the quantity delta x and the new quantity that I'm describing, dx, except for smallness. There is no other difference. Smallness. And indeed it's true, similarly, in every case that I do this, that delta t is in no way dissimilar from dt. Now, when I say small, I appreciate the fact that the smaller I go, the better the approximation. And in my imagination, I can go quite small indeed. As a practical matter, it becomes quite sophisticated, but intellectually I can say, let me make it infinitesimally small, infinitely small, the smallest of the smallest that my imagination can do, and then divided by a quintillion, very, very small. In that case, the interval becomes so small, I've zoomed in so far that the curve is a line. And a line has that remarkable feature that the slope of the line is the same at every point on the line. And by doing so, I will determine the slope at that point instantaneously. So what I'm implying is this, that the velocity which I defined on average as delta x divided by delta t, I will now sort of transform that idea. So I'm not writing an equal sign, I'm putting an arrow. I transform that idea into a differential of position, or differential of displacement rather, pardon me, an infinitesimally small displacement, divided by an infinitesimally small interval of time. That is, I have replaced the notion of average velocity with the notion of instantaneous velocity. And I've been hedging around it here. I've been tiptoeing around the point. But of course, writing that the velocity is the differential of displacement over the differential of time is an issue of calculus. Half of the study of half sort of intellectual half, probably not time half, certainly not the emotional half, but calculus can be divided into two classes, differential calculus and integral calculus. Describing the infinitesimal rates of change of functions is the purview of differential calculus. It has become an issue of calculus to do this. Now, when I take a course in calculus, they have a very sophisticated way of describing these processes very precisely. We do not in calculus say, oh, it's very wee. You do not require a Scottish accent to talk about calculus. It's very wee. It's a very tiny interval of change in time. No, you don't need a Scottish accent to do calculus. They talk about it in terms of theorems and limits and lots of arrows and things going from here and use infinity symbols and whatnot. It's a very sophisticated presentation of what is actually an extraordinarily simple idea. Now, in the intro to our course, I had distributed a set of equation sheets that had useful calculus formulae on. It's to be hoped that at some point we will grow to be experts in calculus, and that we'll use calculus as a tool in the same way that we use algebra. But I have here, for your delight, a series of formulae that show me how to evaluate the instantaneous rates of change of functions. Now, on my equation sheet here, it's written in terms of, in a very mathematical, very mathy kind of way, where we consider y as a function of x, where y has no meaning and x has no meaning. But here, I'm considering that I have some value of x as a function of t, and I'm going to choose today to describe my x as a function of t as a familiar position as a function of time, because we may recently have had conversations about x as a function of t where it looked like this. Consider that the position as a function of time is equal to some constant that I'm going to call alpha multiplied by the time squared minus some other constant that I'll call beta multiplied by the time cubed. If I wanted to know, if I was asked the question, what is the average velocity between this particular time and this particular time? The procedure for doing so would be quite simple. I would simply use this equation for the position as a function of time and find what was the position at the initial time and what was the position at the final time, and then subtract those and divide by the total time. And I would get the velocity on average. And I would have no idea what happened at every instant in between. I have no idea. But now what I'm suggesting is that there is a procedure that is given to me by calculus, and just for giggles, I'm going to write this calculus form on the board here, if I have my glasses to improve my vision. I'm going to write it just as it appears on my equation sheet so that we can interpret it. On my equation sheet, it says d dx, and then in parentheses says x to the n is equal to n times x raised to the n minus 1. Ugh, what gobbledygook. What gobbledygook. If you can look at that and fall in love with it, you may very well be a math person. I look for the meaning in it. To me, what this presentation represents is a description of a known pattern of the rate of change of any function based on the type of function involved. And here, the function that we're describing is a function that is a power series function, monomials raised to a power, x to the n. So it says if you've got an x to the n type situation, then what you should do is bring the exponent down and multiply it, and then demote the exponent by 1. Every once in a while, I get a chuckle by making the sound effect for that. I go, whoa, 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 whoa. Down comes the exponent, demote the exponent, and then we're done. That's how I do calculus. Bang, 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 when I recognize the pattern. It takes time to gain the confidence to see the pattern. It takes, in principle, more time than it should, because the pattern looks very complicated, but it is not. I know the position as a function of time is given by alpha t squared minus beta t cubed, and I would like to know, what is the velocity at any instant in time? It is the question that I have. Tell me a time, and I will tell you exactly the rate at which the position is changing in that instant. Well, in order to do this, it is a feat of calculus. So I will apply the rule. Oh yes, this very sophisticated rule, but down here, what do? I have this 2 that comes down and multiplies. So 2 alpha t. I have brought the 2 down and multiplied, so there's the 2 appears there. And the exponent, which is t squared, has been demoted. 2 minus 1 is 1. Now, traditionally, we don't write the 1. So it can be difficult to spot the pattern when we have these habits of notation that sort of hide the little bits. It's there, right? It's there. It's sort of an idea, like it's there, but you can't see it. It is t to the first. And then I'm subtracting. I'll bring the 3 down and multiply, so 3 times beta, t to the t cubed here. Well, I'll demote the exponent, 3 minus 1 is 2. And so applying a pattern of calculus has made it possible to determine the rate of change of the function. I just did it. I used calculus as a tool. I wasn't thinking deeply about the nature of calculus. I had a thing whose rate of change I needed to determine. I located the pattern on a well-organized sheet of remembrance, and I did it. And I was successful because of the amount of practice that I have doing it. You may not be immediately successful at doing that. In particular, you might be looking at it and say, Scheidly, it seems to me you completely ignored the alpha and you completely ignored the beta, like you didn't even consider them. You looked at the t and saw that it was a square and multiplied by 2 and demoted the exponent, and you didn't even pay any attention to alphas, let alone the fact that alpha surely is some number and we don't know what it is. Yeah, I know. I've learned not to care. I've learned through the process of studying and doing calculus and practicing calculus that multiplicative constants in front don't matter. They just sit there and wait for the process to be over. The calculus starts to happen and the alpha sits there like, oh crap, it just waits for it to be over, and then there the alpha is, still sitting there, untouched, unmolested by the process of calculus. Because calculus is not interested, the rate of change is not interested in things that don't change. Alpha is a constant. It is changeless. So it is unaffected by the application of that calculus. It is immune to it. So now I've found the instantaneous rate of change, and I have what I was asking for. If you tell me a time, I will tell you the rate of change of the position in that instant. Now, the only problem that you have is that nature expresses itself in many different mathematical forms. The application of calculus would have been different. If the position as a function of time were a sine function, the application would have been different. If the position as a function of time were an exponential function, and I would have to go looking for a different rule, that's all. And my success will merely be determined by my practice. That is instantaneous velocity. The velocity determined in an instant when I know the position as a function of time. Scheidly, if I don't know the position as a function of time, is it possible for me to determine what the instantaneous velocity is? Based on what we know so far in our course, no. You must know the position as a function of time, and you must apply calculus, and that's the way the belly button's on that one. However, in future lectures, we'll discover that it's possible for us to understand the rate at which the velocity changes, and from that, discover the velocity at any instant. But that is a discussion from another day, for another day. Now, all of this, it's entirely possible that you've watched it and said, ah, yes, I get it. Consider this situation that I have here, that I've drawn in advance. I have a graph of y position as a function of x position. And I would ask you to please be careful, because it is not position as a function of time. It's a very easy thing for us to become careless about the coordinate axes of a graph that we're looking at. If I look at a graph of position as a function of time, I consider that graph very differently than I do a graph of velocity as a function of time, or in the future, acceleration as a function of time. This is a graph of the y position as a function of the x position. And so now what I'm describing is a two-dimensional problem. A two-dimensional problem. And here's the graph. It's a graph of x squared over 2, or if you like, 1/2 x squared, either way you want to look at it. Its position along the y-axis is a function of x on the x-axis. Y is a function of x. Now, it's perfectly fine there as a mathematical equation, but I want you to imagine that it is a wire, an actual physical wire that is bent into this mathematical shape so that I can place on the wire a bead. So I'm imagining a very short, sort of cylindrical kind of thing. And the wire passes through it. And it can ride upon the line. That means it must have this position as a function of position. The y as a function of x has to be x squared over 2. This thing can't move off the wire. In higher levels of physics, we typically refer to this sort of thing as an equation of constraint, because the bead is constrained to move along a particular path and can't leave it. So the bead can only slide up and down the wire. But I make an observation. I shine some light down from above onto this wire. And as the bead goes along the wire, I'm saying that it generally moves from left to right. As the bead goes along the wire, instead of watching the bead, I watch the shadow of the bead as it goes along the x-axis. And I discover in those observations, maybe there's a meter stick and a stopwatch or something, and I observe the shadow as it goes along the x-axis, and I discover that it moves with constant speed. The shadow moves with constant speed. The bead does not. So what that implies is that the velocity of the bead has a component that is constant. Because when I consider the velocity in 2 dimensions v, what I mean is that there is a component of the velocity that is known as its x component. That is the component of the vector velocity directed along the x-axis, and the x-axis we signify with an I hat. So Vx I hat. Plus another component that's directed along the y-axis that I call Vy j hat, because j hat is the notation that symbolizes the y-axis. Now this is fancy looking, the way that I've written this vector, but the truth of it, it simply means that the velocity of the bead as it travels along the wire has 2 parts. Those parts can be written independently in terms of their instantaneous velocities this way. The x component of the velocity is the derivative of x with respect to time, just as I defined it here in the introduction. And the y component of the velocity, Vy, is the derivative of the y component with respect to time. Now, I haven't described the y-axis motion of anything. I did everything that I've talked about thus far in this lecture in terms of along the x-axis. But what does it matter? Take the x-axis, turn it vertical, call it y. It's the same thing. It's the same idea, the sameness of things. I've been yelling about the sameness of things quite a bit recently. Things are more the same than they are different, is the nature of all things. So I'm making a claim here, and I've written it here below the graph, but just here it is, that the x component of the velocity is equal to a constant, which I'm calling capital C because I used capital C when I originally encountered the problem, and so deep is my romance with this problem that I'm keeping it the way it was presented to me initially. I shine a light down from above and I observe the shadow, and the shadow moves along with constant velocity, which means the horizontal component, the x-axis component of the velocity, apparently is constant. And it's a constant that I call capital C. So over here where I'm doing as I'm presenting the problem to you as it exists, I could write that Vx, which of course is equal to the derivative of x with respect to t, is in fact equal to a constant. Those 2 equations, the same thing. In fact, equal to a constant. Here's my question. If the bead is moving along the wire in such a way that its horizontal velocity, its x-axis velocity is constant, what then is its y-axis velocity? It is a complicated, or it's not complicated, it's sophisticated problem. It's a sophisticated problem, and it's one of these instances that is grounded in a notion that I will continue to stress for all of our time together. If you do not understand how to proceed, write down a thing that is true and try something. Because we want to avoid that idea of, I don't even know how to start. And in this, I think this would be a very excellent case of you don't know where to start. My question is, what is the y component of the velocity? That is Vy. I'll write it just here. Vy equals question mark. If this is true, what is this? You may say, well, Scheidly, are they even related to each other? Maybe the y velocity doesn't care at all what the x velocity is. It is very often true that the motion along the x-axis of a physical system and its motion along the y-axis are unrelated one to the other. That is often true. And it's an idea that I often take advantage of. But in this case, x and y are related to each other by the constraint of the wire upon which the bead must move. So, I'm going to do something a little bit clever that is based on the first equation that appears on our equation sheet. Earlier, I invoked the equation sheet to describe how I take the derivative of a variable raised to a power. When I looked at the equation sheet, I had to skip the first equation. Oh, look at my equation sheet again to see exactly how it's written. Again, written in a very mathy way. It says that the derivative of f, which is just some function of x, with respect to x is equal to, man, this is obvious. It's calculus, so it's very high level, very difficult to understand. Only smart people do it. df dx is equal to df du dx. I mean, come on. There's a du in the numerator and a du in the denominator. They cancel, so this is df dx. It's stunningly obvious. It's stunningly obvious, and yet it gets the name theorem. But it's so painfully obvious. But what is u? Whatever you want it to be. Because if u is y sine theta, if u is x cubed plus 2, if u is a chicken, if u is your grandmother, it doesn't matter. It's going to cancel no matter what u is. So u is freeing. U is liberation. It can be whatever I want. How powerful. Watch me use it. I want to compute Vy. I said, I have no idea how to do that. Yes, you do. Write down a true thing. The velocity of y, or the y component of the total velocity of the thing, the y component is equal to the derivative of y with respect to time. So you have to compute that in order to find the answer. Oh, Scheidly, let's do it some other way. There is no other way. You see, I'm going to take a little aside here. I'll try to do it quickly. Do you see that there's a duck up there on the clock? You may have noticed. It's a duck dressed up for Halloween as Albert Einstein. And the reason why it was gifted to me for some students, because every once in a while I would complain to classrooms full of students that I would teach a fundamental physical thing and then ask them to solve a problem whose nature was obscure. Like, maybe this is not something I saw in class. It was not an example problem that was solved. It was not something that he explicitly talked about. So maybe that fundamental physical law that Scheidly talked about in class doesn't apply here. Scheidly, I can't solve this problem. Why not? Well, Scheidly, this one's a duck. You didn't say anything about ducks. This doesn't solve ducks. And it's very difficult for the student to get their head around the idea that the things that we describe in the lecture are so fundamental that they apply in all cases. If ever I'm up here describing to you a thing that is only limited to a special case, I must say so. But when it comes to the y component of the velocity, this is how it's defined, and it doesn't matter that that's a duck. That's how it's defined. I don't have any choice. This is where it starts. This is where it must start. Scheidly, I don't know where to start. There's only one place. There's only one place. So I'm going to have to compute dy dt. But Scheidly, I don't know y as a function of time. Careful, I don't know it. I know, looking over here at the graph again, y is equal to x squared over 2. I know y as a function of x. Just take the derivative. The worst thing that you could do is say, well, y is equal to x squared over 2, so I'll just bring the 2 down and demote the x, and yay, velocity. If you were to do that, you would be taking the derivative of y with respect to x. You would be taking the derivative of the y-axis position with respect to the x-axis position. I don't know what that is, but I do know what it is. I don't know what that is, but it's not velocity. So you can't just take the derivative of whatever you have lying around. You can't be slapdash. You can't just pull a technique out of your pocket, slam it down, and calculate a thing and hope that it works out. I know that a lot of people have actually succeeded at doing that. You accidentally pull the right technique and you accidentally slap it in the right way and you accidentally get the right result. We don't want to proceed that way. In order to compute this derivative, I need to know what y is as a function of time, and I do not know. So here's what I will do instead, and feel free to admire its cleverness. instead of doing this, I will compute the derivative of y with respect to x and the derivative of x with respect to t. Isn't that exactly the same thing? Isn't that exactly the same thing? Scheidly, I never would have thought to do that. No, of course you wouldn't have. Because you lack the experience with this particular tool. Because you lack experience. This is why you study. This is why you solve problems. This is why you carefully consider every example that you see and every homework problem that you do so that the techniques become known to you. And there's a middle ground where I would have done this. You would have said, hey, Scheidly, that's a good idea. And then there's a technique, there's a stage later on where you go, I see what's up. You get to that level where you go, I see what you're doing. Wham. By the way, I haven't said, this thing has a name. It's called the chain rule, which is a groovy name and kind of makes it easy to remember because couldn't I, here's my original chain rule as it's written on the equation sheet, couldn't I do df, du, du, dz, dz, dq, dq, dx, and just keep on chaining? Why would you keep chaining along and along and along and along? Why would you do that? Well, because I need to get to a point where I've expressed the thing in terms of some derivatives that I can do. My whole problem was that I couldn't compute dy dt because I don't know y as a function of t. But question, can I calculate dy dx? If I know that y is equal to x squared over 2, can I compute dy dx? Yes, now I can use my power rule of differentiation. I can use that to solve it. And so I will. Really quickly, let me show you that I can compute dy dx. I know that one. Dy dx is equal to, exponent comes down, demote the exponent. Now handy, x squared over 2, when I bring the exponent 2 down, there's a 2 waiting for it in the denominator. It cancels. It cancels. Take a moment to verify in your mind that this is in fact x. The derivative of y with respect to x is x. The 2 comes down, cancels that 2 in the denominator, and the exponent is demoted. 2 minus 1 is 1. So now I know the derivative of y with respect to x. Do I know the derivative of x with respect to t? It's laughable. Not only do I know it, it is what Vx is. It is Vx. That's what Vx is. dx dt. I was told. I don't even have to compute it. I was told. In the problem statement, I was told that dx dt is equal to c. So here's what I've done. Here's the strategy. Here's the way it works when I'm solving high-level problems. I have a question to which I do not understand the answer. So I write down the true thing, and here's the true thing, and I have no choice but to confront it. And so I take this derivative, which I cannot do, and I separate it into 2 derivatives that I can. So now, I'll simply state the obvious. If you don't mind, I'll put the variable second because that's a very sensible thing to do. And I have found the y component of the velocity. Not as a function of time, not as a function of time, but as a function of x. Not as a function of time, but as a function of x. Can I write it as a function of time? Well, in order to do that, I would have to be able to write x as a function of time. Well, x as a function of time is a constant. X as a function of time is a constant, or I'm sorry, pardon me. I have to take that back. The x velocity is constant. And so therefore, going back to this idea that x is equal to x naught plus v times t, if the constant x velocity is c, then x as a function of time is equal to c times t. X as a function of time is c times t. And so the y velocity as a function of time is c squared times t. While it is true that the x component of the velocity is a constant, the y component of the velocity increases in time. So, as this bead moves along this axis, and its shadow moves with constant speed, its y velocity, the part of its velocity that is taking it upward, increases linearly in time. And the combination of those velocities results in following the parabolic path that is the wire.